Ancient Romans believed that our universe suddenly started with chaos, a huge mass of mixed elements. Early Christianity and Judaism believed that the world appeared out of chaos with the help of an almighty God. What's curious is that a recent scientific experiment has proved that the creation of the universe indeed happened this way. So, could old myths and the earliest religions be closer to the truth than our modern understanding of the world? In general, the answer is yes, but they were wrong about the details. Researchers determined that the chaos that existed before the creation of our universe is lots of quantum particles in a superposition, and the almighty God that molded this chaos into our reality was a black hole. So, how was our world created after all? Can we exist in two different places simultaneously? And what if even such a basic thing as time turns out to be unstable and unpredictable? At first glance, the rules of the quantum world have nothing in common with our day-to-day lives, where a couple of seconds ago, you were busy trying to find something to watch while eating your nuggets. Here, you don't have to worry that if you turn away from the crispy chicken on the plate, it may turn into your neighbor's cat or radioactive uranium. Meanwhile, quantum particles behave as waves, a set of probabilities, right until the arrival of an observer. And solely after that, the particle becomes something particular that can be measured. But in our world, reality exists no matter if anyone observes it or not. Or am I wrong? Actually, the quantum world isn't just an imaginary model that physicists use to run their experiments. It's our reality. The entire universe consists of tiny quantum particles. It looks like it used to exist as a set of waves in a superposition before there appeared an observer and our reality took its present form. But who is this observer? A group of scientists from the University of Chicago and Princeton University tried to find the clue. The team included Robert Walk, Gautam Satishchandran, and Dane Danielson, who started wondering what could happen if a supposed observer is placed beyond a black hole event horizon. The thing is, anything that enters this area can never come back, including information. Consequently, information can travel from a quantum particle to an observer inside a black hole. But it can't be the other way around, right? At this point, the black hole information paradox helped scientists out. The thing is, these space giants gradually evaporate. They emit a stream of elementary particles known as Hawking radiation and slowly shrink in size and disappear. If information can't escape the event horizon and the black hole gradually evaporates, it means that information enclosed within it disappears too. The problem is that it can't disappear to nothing or come from nowhere. Otherwise, it contradicts the fundamental principles of quantum mechanics. In 2016, a scientific team led by Stephen Hawking found out what actually happens there. When a particle falls into a black hole, information about it doesn't vanish beyond the event horizon. It stays around the black hole as very weak radiation. The researchers called this information-rich halo soft hair. In 2023, researchers Wald, Satishchandran, and Danielson, mentioned at the beginning of the video, assumed that this hair functions as an observer in relation to particles beyond the event horizon. They think a particle leaves a trace of information not only when it crosses the event horizon. Soft hair records its further movements into the depths of the black hole too. That's why under the influence of this radiation, all superpositions outside the event horizon will switch from the ambiguity of the quantum world to our reality. It seems that the black hole is that very almighty God that forces the quantum particles in the universe to take a certain physical shape. But if so, wouldn't our universe look like a cluster of aisles around black holes lost in endless space of quantum particles in a superposition? In fact, no, because the concept of distance is inherent only to our reality and has nothing to do with the quantum world. An observer and a particle can instantly exchange information at any distance. Experiments have repeatedly confirmed this fact. For instance, in 2017, Chinese satellite Mikias transmitted entangled photons from orbit to 3 ground stations located no less than 1,200 kilometers away from each other. When experts at one station acted as an observer and measured one of the photons, the particles in the other locations also lost their quantum properties. By the way, this distance is far from the limit. Any corner of the universe may as well be connected to the hair of one of the black holes that shapes our reality. However, there is a pressing problem. As I've already told you, black holes gradually evaporate. This is a very slow process. For example, a supermassive black hole in the center of our galaxy called Sagittarius A star will completely disappear only in one googol of years. At least, scientists think so. But in truth, quite recently, these mysterious space objects have brought us a lot of surprises. In 2022 alone, astronomers found the first wandering black hole in history that's traveling across the Milky Way. They also witnessed an unexpected magnetic flip executed by one of these space giants. Who knows, maybe in the near future, scientists will realize that these objects evaporate much faster than we expected. And what will happen if black holes disappear and our universe ends up without an observer? When the link between an observer and a particle is destroyed, the quantum object returns to a superposition state. In this case, as soon as the black hole fades away, the universe, together with people, will just cease to exist. Or not. In fact, a quantum particle may be observed by, for example, another particle. The question is, what physical shape would the world around us assume if random particles acted as its observer? It turns out that if this scenario comes true, our world will turn into chaos. Although there are scientists who believe that it's not going to happen. Not only that, physicist Roger Penrose from Oxford University is sure that we don't need any observers at all. In the late 20th century, he reached a conclusion paralleling that of Lajos Diósi, a researcher from a Hungarian university. They both came to think that quantum particles take their shape because of gravity. Simply put, when a quantum object is in a superposition, all its possible states somehow communicate with each other with the help of gravitational pull. Therefore, the particle begins observing itself and assumes one of the possible forms, although this theory contradicts the results of scientific experiments. The point is, preserving quantum superposition in the laboratory isn't an easy task. To make a particle remain in this state, it needs to be completely isolated from the effects of the environment. Oscar Painter, professor of applied physics at the California Institute of Technology, jokes that it's better not to look at your experiment testing superposition or breathe on it. But usually, physicists succeed in creating the right conditions for the particle. For example, if you throw it in a vacuum, it'll help to avoid the impact of gas molecules. However, even a vacuum can't neutralize the effects of gravity. Penrose and Diósi believe that in this case, superposition wouldn't be possible, and the gravitational force would make the particle collapse into our reality. But it doesn't happen, at least immediately. This means we need an observer after all, and the absence of black holes will influence the entire universe as we know it. Or will it not? In their research, Wald, Satishchandran, and Danielson mention another potential candidate to try on the role of an observer. It turns out that the world may be supervised by itself, or more precisely, its edge. The point is, quantum particles can be influenced by absolutely any horizon that lets information travel in only one direction, as it does, for example, with a black hole event horizon that's impossible to escape, or the Ridddle horizon. Imagine you're moving through space with constant acceleration. At some point, you become so fast that even a photon traveling at the speed of light can't catch up with you. At this moment, an imaginary boundary will appear behind you. Nothing in the world will be able to cross it because nothing can move faster than light. Now, you're doomed to loneliness, and the line separating you from the universe is called the Ridddle horizon. Despite this, the main frontier in outer space is the cosmological horizon, or the edge of the observable universe. It's situated over 45 billion light-years away from Earth. The time a photon needs to cover the distance from our planet to the universe's edge equals the age of the universe itself. Therefore, information hidden beyond its edge will never reach us. That's like a black hole turned inside out. And even though scientists don't fully understand how it works, we can breathe a sigh of relief, since even if all black holes disappear, our universe won't shatter into a superposition of infinite quantum waves. There will always be something to observe us. This is assuming that we haven't been wrong from the start, of course. Frankly speaking, physicists are still unsure what mechanism causes quantum particles to collapse or take their real form. A quantum particle in a superposition is a whole bunch of probabilities. When an observer appears, absolutely any of them can call the tune. How exactly these particles give rise to our reality has been a subject of controversy among scientists for around a century. In 1926, Erwin Schrödinger proposed a mathematical equation to predict the future behavior of a quantum particle. Sounds quite logical, but it doesn't work. In practice, it becomes clear that the equation can reveal the probability of a particle turning into, let's say, Mars compared to its chances of becoming Earth. But what exactly it'll transform into during a particular test can't be predicted at all. To describe this randomness, Albert Einstein came up with a metaphor of God playing dice. In 1986, a team of Italian physicists named Girardi, Rimini, and Weber brought even more chaos to the math of quantum mechanics. They suggested that particles transform spontaneously without any involvement of an observer. How quickly they collapse into real things depends on the size of the system. In other words, if we take a separate atom in a superposition trapped in a vacuum in the middle of cosmic nowhere, it may remain in this state for a very long time. For example, if we take atoms of Saturn's rings, they instantly shift from the quantum world to our reality and form, well, Saturn's rings. But still, something didn't add up. A bit later, physicist Philip Pearl refined this theory. He assumed that the collapse wasn't a sudden jump from the quantum world into reality, but rather a continuous process. Thus, a particle doesn't just become a particular object once, but keeps collapsing non-stop and going through changes in real time. This could explain why every attempt to measure this particle in a superposition brings an observer a different result. This model was further developed in 1990, although in truth its framework appeared a long time ago, in the 15th century. Rosicrucian teachings promoted a similar idea of how our reality works. Members of this secret society thought that, contrary to what the Bible teaches us, the world couldn't possibly have been made in just 6 days. Instead, Rosicrucians believed that creation was a never-ending process, not just a single event from the remote past. According to them, this process isn't finished yet and continues, literally, every second. At the same time, neither Rosicrucian teachings nor the continuous spontaneous localization model explains how our reality is getting formed and why it looks the way it looks. But what if quantum particles don't collapse at all and always remain in a superposition? In 1957, physicist Hugh Everett asserted that this collapse is just an illusion. Instead, when an observer interacts with a quantum wave, the universe splits into multiple branches, and in each of them, the measurement result will be different. Simply put, Everett thought there's an infinite number of parallel worlds where quantum particle acquires one of the possible forms of reality. This means if the scientist was right, you and I live in one of these universes. If so, what do all the other worlds look like? And what could happen to our reality if the observer in charge of creating it accidentally blinked? In fact, humanity hasn't made much progress in studying its home universe. We've still yet to determine if it's flat or asymmetrical, how big it really is, and how most of its elements work. But as strange as it may sound, scientists tend to think it's pretty simple. Let me explain. Imagine standing in a room right now. Are you cold or hot? If you measure the temperature and then swap 2 random hydrogen and helium atoms in this room, would it help you feel warmer? Probably not, because it won't affect the ambient temperature in any way. Even if you shuffle all the air molecules around, nothing will change. Besides, the more options of their arrangement are present, the higher the entropy is. You should know that in our universe, entropy is high. That's why the probability of its appearance in other worlds is also high. Physicist Neil Turok from the University of Edinburgh and Latham Boyle from the Perimeter Institute for Theoretical Physics have concluded that our universe looks the way it looks for the same reason air uniformly fills the room instead of staying in one corner. Even weirder variations in the design of the universe are possible. but unlikely. And it sounds plausible, as it's hard to support the existence of a world where a flap of a butterfly's wing or movement of a helium atom can trigger supernova explosions or mass extinctions. That's why if we make 100 random worlds, around 98 of them will be almost exact copies of ours. Long story short, if the observer responsible for creating our world suddenly blinked and a different reality replaced ours, we wouldn't even notice, because an alternative world would be very similar to the one we're used to, with minor differences. For example, there'll be no mosquitoes on the new Earth, or Saturn will lose one of its rings. At worst, the continent of Australia will never be formed. Although, if this lottery really fails us, we may be unlucky enough to get a dreadful reality that haunts scientists in their nightmares. For instance, we may find ourselves in a de Sitter universe entirely composed of dark energy. So far, this universe can only exist in researchers' imaginations. They use it for thought experiments. And yet, the chance it may be real is low, but not zero. So what does a de Sitter universe look like? The first thing to attract your attention if you get to this place will be total darkness. None of the structures we know can exist in a reality composed of only dark energy, so there won't be stars, nebulas, or black holes. The only process that will be possible in this universe is infinite expansion. But actually, our reality could look even stranger, because not only its physical parameters could be unusual, even the configuration of space-time could work differently. More than a century ago, Einstein's general theory of relativity showed that space and time are inseparable things that together weave the fabric of reality. Under extreme conditions, space-time can get curved and form black holes. Over decades, this process was the main focus of research of Gary Gibbons and Stephen Hawking. The cosmologists arrived at shocking conclusions. Remember, I've told you there's no notion of space in the quantum world. Well, the same goes for the idea of time. There's even a special method called Wick rotation that lets scientists use the so-called imaginary time. In simple words, if we imagine our regular time as a line stretching from the past to the future, imaginary time will cross it perpendicularly. You're not going to believe it, but for scientists, this imaginary time is a means of mathematical simplification. It may sound absurd, but this approach let Gibbons and Hawking become the first physicists in history to calculate the temperature and entropy of a black hole and undermine established beliefs about space and time. The scientists concluded that space-time, as such, isn't a single entity, but small particles. In this case, in some parallel realities, they could also modify their properties depending on an observer. Now, just imagine what happens if the observer blinks. Bam! And everything is different. Matter could suddenly exist in several points in space simultaneously. An exact copy of you could be watching this very video on a distant planet somewhere near Betelgeuse that exploded as a supernova and became a yellow dwarf long ago. The bad news is that both of you are unlikely to stay with me to the end, as in this reality, time is made up of quantum particles in a superposition. Whether it goes forward or backward depends on the observer. But no worries, you'll anyway disintegrate into atoms in 3, 2, 56, 1. It's so chaotic because the matter existing in two places simultaneously is extremely unstable. But I have good news too. There's no need to worry you'll get sucked up by a black hole. In this world, they don't absorb everything within reach, but quite the contrary, push things out and radiate light. Plus, the universe is now shrinking instead of expanding. However, space-time is so anomalous here that the world cannot achieve singularity. These hopeless attempts of the universe may remind you of water ripples caused by a pebble, but in reverse. Fortunately for us, the universe's edge is a reliable observer that's unlikely to disappear anywhere or start blinking. That means we're in safe hands, at least until scientists discover some new unbelievable truth about our world. And yet, I have one more question to ask. As I've already mentioned, the edge of the observable universe reminds me of an event horizon. It looks like we live in an inside-out black hole watching us from a distance. But what if it has other funny worlds to spy on? What if there's an unknown universe beyond the cosmological horizon? What could it look like? I suggest you check my video about Boltzmann brains to learn why this universe may prove to be a giant neural network or an enormous conscious being? Leave a comment and share your vision of alternate universes.